Welcome back to the channel that asks the big questions. What is today? We're tackling something that powers our entire modern world, yet remains largely invisible and, let's be honest, a little bit mysterious. It's the silent force lighting up your screens, chilling your drinks, and making that toaster pop. We're asking, what is electricity and how does it know where to go? Have you ever flicked a light switch or plugged in your phone and just for a second wondered, what is this stuff? And more importantly, how in the world does it know exactly where to go? Does it have a tiny little GPS navigating through our walls? Let's electrify our minds and find out. What is electricity? The basics. At its most fundamental level, electricity is about tiny, incredibly energetic particles called electrons. Imagine them as the most enthusiastic, hyperactive commuters you've ever seen. They don't like standing still. They have a natural urge to move, to jump, to get from one place to another. Electricity, pure and simple, is the movement of these electrons. Millions upon millions of them, flowing in an organized way. It's not creating them out of thin air. It's taking existing electrons and giving them a collective shove, making them march in a certain direction. Think of it like a giant, invisible parade of microscopic movers and shakers. The flow, current, voltage, resistance. Now, when we talk about electricity, there are three key players in this electron parade. First, there's current. This is simply the number of electrons passing a point over a certain time. In our parade analogy, it's how many marchers are passing you every second. If you have a lot of marchers, you have high current. Then there's voltage. This is the push, or the pressure that gets the electrons moving in the first place. You can think of it like the enthusiasm of the parade leader, or the steepness of a hill that encourages marchers to flow downhill. Higher voltage means a stronger push. And finally, resistance. This is anything that tries to slow the electrons down. It's like speed bumps in the road, or that one slow marcher who keeps stopping for selfies. Materials that allow electrons to flow easily, like copper wires, have low resistance. Materials that block them, like rubber or plastic, have high resistance. We call those insulators. So, electricity isn't just about electrons. It's about their quantity current, the force driving them voltage, and the obstacles they face resistance. Where does it come from? Generating the push. So, where do we get this push to make electrons move? Well, we don't create electrons. They're already part of atoms. What we do is give them the energy to detach from their atoms and start flowing. This is the job of a power plant. Whether it's a hydroelectric dam using falling water, a wind turbine catching the breeze, solar panels capturing sunlight, or a power station burning coal or using nuclear fission, the ultimate goal is often the same: to spin a giant magnet inside a coil of wire. This spinning motion, through the magic of electromagnetism, creates that powerful push, the voltage that gets those electrons jumping and flowing through our wires. It's essentially a massive electron pump, constantly working to keep the parade moving. How does it know where to go? The circuit's commands. All right, this is the million-dollar question. How does electricity know where to go? Does it have a tiny brain? A map? The simple, non-sentient answer is, it doesn't know in the way we do. Electricity follows the ironclad laws of physics. Specifically, it follows the path of least resistance within a closed circuit. Imagine those enthusiastic electron commuters. They are constantly looking for a complete loop, a full circle to travel. From their starting point at the power plant, through the wires, through your appliance, and back to the power plant. This complete loop is called a circuit. If there's a complete, unbroken path, the electrons will flow. If that path is broken, say, by an open switch, a cut wire, or a grumpy electron who decided to take an unscheduled coffee break. The flow stops immediately. No loop, no flow. It's like a perpetual motion machine, but only if the track is fully connected. The electrons are drawn forward by the lower electrical potential at the other end of the circuit, like water always flowing downhill. The grand highway, the electrical grid. This incredibly complex system of complete loops is what we call the electrical grid. After electrons are given their initial push at the power plant, that voltage is often stepped up by a special device called a transformer. Why? Because higher voltage means less energy is lost when sending electricity over very long distances. Think of it like packaging many small boxes into one giant cargo container, more efficient for long-haul shipping. These supercharged electrons then zip along massive transmission lines on those towering metal structures you see crisscrossing the countryside. When they get closer to populated areas, they go through substations, where transformers step down the voltage to safer, more manageable levels. Finally, they travel along smaller distribution lines, often on wooden poles, right into your neighborhood, into your home and the appliance's job. Before it enters your house, the voltage is stepped down one last time by a transformer on a pole or a pad-mounted box. It then flows into your electrical panel, where it's divided into separate circuits, each protected by a circuit breaker, essentially a safety valve that pops if too many electrons try to crowd onto one path. From the panel, wires run behind your walls to outlets and light fixtures. When you plug in an appliance, you complete that circuit. The electricity flows from the outlet through the appliance and back out through another wire in the plug, completing the loop. Your appliance doesn't store electricity. It uses the flow of electrons. In a light bulb, the electrons encounter a thin filament with high resistance, causing it to heat up and glow. In a motor, electromagnetic forces convert electrical energy into mechanical movement. The electrons don't know they're lighting a bulb or spinning a fan. They simply follow the path provided by the circuit and release energy as they encounter resistance. The ingenuity of the invisible worker. So, to recap, electricity doesn't think. It simply obeys the fundamental laws of physics. We, as humans, have figured out those laws and designed incredibly intricate systems. The power plants, the transformers, the wires, the switches, the appliances, to create precise, controlled paths for those electrons to follow. Every wire is a designated lane. Every switch is a gatekeeper. Every appliance is a purpose-built destination within the electron's looping journey. When we say electricity knows where to go, what we really mean is that we've engineered its entire route, meticulously planning every turn and stop, ensuring it always finds a complete circuit to follow. It's a testament to human ingenuity, taking an invisible, natural phenomenon and harnessing it to power our entire world. It's a silent, tireless worker, always ready to go, as long as we give it a clear path. So next time you flip a switch, remember, you're not just turning on a light, you're completing an incredible, invisible journey for countless, enthusiastic electrons, guided by the genius of physics and human engineering, effortlessly following the path laid out for them. If you enjoyed this electrifying journey into the heart of what powers our lives, please consider giving us a like, subscribing to the What Is channel, and hitting that notification bell so you don't miss our next deep dive. As always, keep asking what is, because there's always more to learn. Thanks for watching.